Now that we've defined cardinality and talked about what it means to be a countable set, we're going to talk about the proof of why R is not countable. So we're going to review the definition of what it means to be a countable set. We're going to set up the proof by contradiction, which is how we're going to prove the real numbers are uncountable by assuming that they are countable. And then we're going to present a strategy for the proof and determine some necessary lemmas that you're going to work on in the activities. And you may have noticed I said a proof that R is not countable. If you look in your textbook, it gives you a different proof. I'm not a fan of that one because it depends on real numbers having a decimal representation. And we haven't really proven that real numbers have a decimal representation. This proof does not depend on that. But you're welcome to look at the proof in the book. So recall that if A is a set, we say that A is countably infinite if A has the same cardinality as the natural numbers. We say that A is countable if it's either finite or countably infinite. And we say that A is uncountable if A is infinite but not countable. So recall that we know that the rational numbers are countable. If we haven't proven that, ask me to do it in class. I'm happy to do that. Which, to me anyway, is pretty astonishing, right? The question is, what about the real numbers? Well, that would require us to have a function f from the natural numbers to the real numbers that is 1 to 1 and onto. So let's assume there is one, see if we can find a contradiction. Well, if there is a contradiction, that's likely to be that f is not onto because, again, the idea is that R has more elements in some sense. It has a bigger cardinality than n, so that it's going to have some elements that are not in the range of the function. So we're going to try to prove that there is a real number that is at least one real number that's not in the range of f. So what is the range of f? Well, again, your inputs are the natural numbers. So you have f of 1, f of 2, f of 3, f of 4, etc. You got a sequence, basically, right? So let's see if we can find some big sets of real numbers that avoid f1, and then maybe avoid f1 and f2, and then maybe avoid f1 and f2 and f3, and hope we can somehow generate a bunch of sets that keep on going, and eventually avoid all those outputs. So the idea is to winnow down our set into something that's not empty, but that includes nothing from the range. So can we think maybe of some big sets? And by big sets, I mean sets that contain a lot of real numbers that we can use for this. Well, intervals seem like a good idea. So let's see how we can use intervals to find lots of real numbers that don't include the outputs. Let's just start with f of 1. That's our first output. Let's see, and f of 1 is just sitting somewhere on the real number line. And let's see if we can somehow find an interval that doesn't include f1. Well, that's pretty easy. Just move to the left or move to the right, right? We want to find a closed interval I1. There, we have one to the left, I1. Just make sure that the right endpoint of the interval is to the left of f1. So that's not so bad. Well, what happens when we add an f2? Now we want an interval that doesn't contain f1 and also doesn't contain f2. Well, one thing that we can try doing is finding an interval inside I1, because that would automatically not include f1, and see if we can make it small enough so that it doesn't include f2. All right, so where is f2? F2, well, one of the places f2 can be is sitting somewhere in I1. That's pretty inconvenient. But if you look, we can exclude f2 with an interval inside that I1, like that, right? And even though that interval is a lot smaller than I1, it still contains infinitely many numbers. So it still contains a ton of numbers. So that is what happens if f2 is in I1. What if f2 is not in I1? Well, that actually is easier because f2 is already outside I1, so is f1. So we can just say I2 is equal to I1, right? That is an interval that excludes both f1 and f2. And that's all we were looking for in the first place. So the idea is to continue doing this until you get all the outputs excluded from the intervals. Right? So we're going to define a sequence of closed intervals I1, I2, I3, etc., where in plus 1 is contained in I sub n, and also make it so that the first f of 1 through f of n are not in that in. Then we're going to define I to be the intersection of all those intervals, because if we take the intersection of all those intervals, that presumably will exclude all the outputs. Then we can make the claim that each number in I is not in the range of f, and that will give us our contradiction. Well, as long as I is not empty. So we got to prove that each number in I is not in the range of f, and we have to prove that I actually has a number in it. So we have a few missing details. We're going to fill those in with some lemmas. We need to prove that we can exclude f of n from in. We've already excluded all the others from in because they are not included in the previous intervals. So we just got to exclude f of n as long as in is contained in the previous interval in minus 1. This lemma is going to help us with that one. You're going to prove this one in class. If you have two real numbers a and b with a less than b, and if you let x be any number in that closed interval between a and b, then there exists a closed interval j contained in the closed interval ab with x not in j. So you're going to prove that, and that's going to help us recursively build those intervals. Recall we're going to let I be the intersection of all those intervals that exclude the various outputs, right? We need to know that I is not empty. That means we're going to have to prove that the set I is of the form, I'm going to say the closed interval AB, where A is less than or equal to B, except that kind of bothers me because if A is equal to B, that only includes 1 point. It's not an interval. I'm going to say closed interval AB with the understanding that when A is less than or equal to B, I know it's not an interval, but it's not empty. It does have a point in it, and that's what's important. So we're going to need to use the left points of the INs to find A, and we're going to use the right endpoints of INs to find B, using the concepts of infimum and supremum. You'll see when we get there. All right, so now I think you're set up to work on the activities for uncountably of the real numbers. You just go to the link below this video. It includes some prompts to help you work on all those lemmas. Then we're going to come back for the next video and do a formal proof of the uncountability.